chemistry book, and we're in chapter 15 in the first section, and we're talking about acids and bases, and we got to the point of how we're supposed to name acids and bases. And so the two principles are, for first of all, for those acid and bases that are binary acid, that means there's just two. They're just basically with hydrogen, with a metal type hydrogen here, and these are pretty easy. This HF would be this is hydrogen and fluoride. This would be hydrofluoric, how we add ic to the end of it. And this is hydrogen and chloride, hydrochloric. Hydrogen and iodine, hydroiodic. And on to hydrogen seleniide, hydroselenic acid, right? So, but that seems pretty easy. But then we also have oxide, or polyatoms that have oxygen in them. And these are kind of listed on the table of on page 40. You can go back there. But there's these, they called them oxyacids because they have oxygen in it, and we had some examples. So here's the examples of some acids. So if you have, this is called, it's a poly because it has all of these elements in this molecule, and you call it phosphate. We call that phosphate. We call this one here with the SO4 sulfate. This is called sulfite. And so how do we change these to the acid? So phosphate, you turn the ATE into IIC. Always ate, I ate ic. I ate ic, so phosphoric acid. Now this is ITE. I ate ic and ite us. Ite us, ate ic and ite us. So anyway, we have sulfite is turned to OUS. So there's two different endings. One is ic and one is us. And so ate ic, sulfate to sulfuric acid, hypochlorite to a hypochlorous acid, chlorate, ate to ic, chloric acid, perchlorite to perchloric acid. See how it's just ate ic, itus. Because I think ate it and it was icky, it ate us. Ite us. So anyway, however you want to remember it. So now let's go on to the example, because this is probably going to be on your quiz maybe. So you want to name each of the following molecular compounds as acids. So in these, you're going to have to go back to that table to find out if you don't know what the name is, because these look like all polyatomic in that polyatomic atom. We look back and find the name in that table on page 40. I'm not going to go back there because it'll take me a while to go all the way back. Well, here, let's see if we can go back there easily. Let me see. So let's see. Maybe not. Well, anyway, it's on page 40. It has all these different. Let's see if I can move it back without having problems. Okay. Here we go. Got to it. So here are, remember, we're supposed to memorize these, but it's very hard to remember. Some of them are elements which are very easy here, but here we have ammonium. NH4 is ammonium. On to here, what's another one, a polyatomic one here? Oh, acetate is C2H03. We call that acetate. Here's bicarb. So we have carbon in there and oxygen. Bicarbonate, they call it. And here's bisulfate. Sulfate, you call it. So it's ate, and onto here, just kind of recognizing these major ones. This is the hydroxide ion that we've been dealing with, right? Here's phosphate right here. And on down, we have carbonate. We have another, this is hydrogen phosphate down here, depending on the ions. These are two charges down here, sulfate, sulfide, silicate, so all of these are what we're going to be dealing with when we're trying to label. So let's go back, see if I can go back to the right place. So without having a problem. Mm-hmm. 15. Okay. All right, here we are. That wasn't too hard to go back there. Well, here we go. We're going to look at this. Since HNO2 is an oxyacid, that's what we were talking about, the oxyacid has oxygen in it, we call it the nitrite ion. So this is nitrite. Now, ite is always changed to OUS, remember? We have 8, so 8 us and ite os. Ite us. Our 8 is changed to ick and ite to us. Okay? So anyway, so that'll be changed to adding that word, we're going to add the word, if it's nitrite, ite, we're going to add OUS. The next one, if it's, this is called acetate. We looked at that in that table there, and it's called acetate, and this is another polyatomic oxygen type molecule, and it's called basically called acetate. So now we have 8, we're going to change it to ick, so and then add acid. And carbonate, this is the carbonate polyatom, and so it's going to 8, it's going to be changed to ick, so and then add the acid, carbonic acid. This is going to be called carbonic acid. Just how to name these acids. So that's not too hard. Just remember adding basically 8 ick, I ate ick, and ite us. 8 ick, ite us. So now we're going to this section here is a little different. It's going to be talking about polyprotic acids. So what does this mean? So we have like hydrochloric acid and nitric acid right here. Here's hydrochloric acid and nitric acid. And that they only lose 1 proton. So if they lose only one proton, they call them monoprotic acid. But some of them lose 2 hydrogen protons. If they lose 2 hydrogen protons, they're going to be called diprotic. That means losing 2. Now, if they lose 3, they're going to be called triprotic acids. So this is not hard. Just know, okay, one of them just lost 1 hydrogen, so that's a monoprotic. Now, it lost 2 hydrogens, it's going to be a diprotic, and if it lost 3, which is very rare, it's going to be a triprotic. So here's the formula here of these 4. Here's a monoprotic. You see hydrochloric acid, basic and it's losing just 1. It's losing that hydrogen. But you can just look at these very easily. It looks complicated, but the way I do is I just look here very easily, and you'll see this is just 1. So if there's only 1 hydrogen in the front, it's going to be mono. Look at this equation. It has 2 hydrogen. If there's 2 hydrogen in the front, and they're going to lose those hydrogen, which they do, the 2 hydrogen, it's going to be diprotic. Look at this. This here, it's going to have 3, H3. 3 hydrogen, it's triprotic. So it can lose 3 hydrogen. Just look at the first letter there, and you'll see if it's mono, or it's di with 2, or if it's with 3 there. So both diprotic and triprotic are poly. That means poly means have more than 1. So you can also call them polyprotic acids. So it says when writing the formula, the hydrogens are usually written first, and most of the time you put the hydrogen first. So that's how come you can see it right quickly there. So you can look and see the hydrogen being first. You can find out if it's. And remember, we're always going to talk about the H, which is the hydrogen. So acidic and basic anhydrides. So oxygen tends to form ionic compounds with metals. So, and these metals, of course, are on the which side? The metals are on the left side. So when you see different metals, whether it be the metals in column 1 or column 2, you know, these a lot of times combine with oxygen, right? And so many of these oxides can be classified as acidic, based depending on how they react with water. So basically, acidic means they're going to let go of hydronium, hydrogen ion. So like when carbon, it says when carbon molecules dissolve in water, some of them react with water. So we have carbon and water to form carbonic acid. This is very important because it's actually goes on in our body too. So we have a carbon dioxide here reacting with water, and we get carbonic acid. This is a buffer system in our body. So then on to which ionize to a small extent in water to hydronium ions. So here we have this, it goes into another process, carbonic acid and water, and it's producing the acidic solution here, and this is the hydronium ion that really tells that it's very acidic. So it gets even more acidic here in the midst of this reaction with water. An oxide that combines with water to form an acid is called an acidic anhydride. So just think, when water is combining with either carbon dioxide or something that's going to be called an anhydride. Anhydride gives you a clear, it means without, an means without water, but as it's combining of that acid, therefore carbon dioxide is going to be the acidic anhydride of the carbonic acid. So, and it's same with sulfur dioxide here. So here's in the midst, we have oxygen and sulfur dioxide here combining with water again, and you're going to get hydrogen sulfate, this aqueous solution, and onto 3. See how they're combining? Basically, this whole combining, as you see there, as they're combining with water, they call these anhydrides because they're combining with water. In general, non-metal oxides tend to be acidic anhydrides. So if you just the name, basically knowing just the name anhydride has to do with oxides combining with water to form anhydrides. So here's an example here, an acidic anhydride here, sulfur dioxide, which we just went over there. Carbonic acid, just think it has to do with oxygen and combining with water. So an oxygen type molecule combining with water is an anhydride. Just think hydride is water too. Hydride either represents hydrogen or H2O, which is water. You say you hydrolyze something, you're putting water to it. So that's just what we need to know. So here's an ionic metal oxide as sodium oxide here, and it's added to water. So it reacts to form hydrogen oxide. So we have sodium oxide here. It's anhydride. It's reacting with water to form, basically to form hydroxide atoms. Here's the OH, meaning hydroxide atoms. So here's a basic picture of an anhydride. This is calcium oxygen. As it's reacting, it's turning. You see how it's turning a color here. So this really fits into the Arrhenius base. So thus, this situation here, when you have hydroxide ions, OH, means it's a base. So here we have this calcium oxygen is the same as, see if you see, calcium and is taking the place of sodium here. But otherwise, both of them coming through as a metal type reaction and getting oxygen, they're both turning into OH. You see the OH? That means they're getting more basic. So this NaO is a basic anhydride as it reacts with water to form a base. So we can form a base or an acid. So let's go back to that other one to show you, just to review here. So here we have, as they're forming, they're getting acids because there's an extra hydrogen here that makes it an acid. These are acidic anhydrides. Just remember, anhydrides mean they're reacting through water and not onto. But this is a non-metal situation in this one. So, and here they're reacting and getting OH in the midst of the atom. So the OH meaning it's going to be base, right? So depending if it's hydrogen or it's hydroxide, which is OH. So this whole section has to do with you're recognizing bases and acids. So you recognize an acid by the hydronium H3. Remember, with the instead of H2O, you have H3O. Then you know it's an acid. So because you added in hydrogen. But if you have something with OH instead at the end, that's going to mean it's a base. So in general, the oxides of alkali and alkaline earth metals are basic anhydrides. So these are metals. So if you have alkali or alkaline earth metal and react it with water, you're going to get anhydride. And so these you'll see, and a lot of times these produce salts too, you'll see in. Oxides of many other metals are insoluble and do not react with water. There's a lot of them. But the ones that react with water are going to be called, what did I tell you? Anhydrides, meaning water. So let's go over your concept review real quick, because this can get kind of complicated, I know. You're thinking, oh, I hope I can get all this stuff. But there's some basic things we need to know. And a lot of times they're in the concept review. So let's go over the concept review just so that you can get these in your head. So first of all, it says list 3 properties of acids and bases. Well, 3 properties of acids are what? Acids are sour, and they usually can react with certain metals and produce hydrogen gas. They also react, what color to litmus paper? Red. Acid is red. Properties of bases. Bases are bitter, B, and they react as a slippery feeling. They can also neutralize acids, we know that, but they're on the litmus paper, base turns blue. So list those 3 properties. So it says differentiate between Arrhenius and Bronsted-Lowry. Arrhenius have to do with the hydrogen, H, and OH. So basically they're saying if you have hydrogen, if it produces hydrogen, it's going to be acid. If it produces hydroxide, it's going to be base. That's the Arrhenius. Now the Bronsted-Lowry accepts a proton. You can see the difference is the Bronsted-Lowry, there's a couple differences, but when it accepts a proton, basically accepting the proton of hydrogen, it's going to become more hydrogen, right? And so in that situation, it's going to be an acid. It accepts a proton. Now, if it was a base, it would get rid of it's actually getting rid of a proton, so of hydrogen. So anyway, the differentiate is the Arrhenius has the H and the OH, and the Bronsted-Lowry is actually accepting, a proton, and produces it. So you're talking about, just think of Bronsted is talking about a proton, and Arrhenius is talking about the hydrogen ion. That's basically the main difference. And you can see that table as you go. In what form do protons generally exist in aqueous solutions? So what form do they usually exist? And that's that very common form. And that's called the hydronium ion, H3O. Let's see if you can see it on my paper here. I circle it. The hydronium ion is H3O. So H, or I should say, H with the 3 and then O. And that's the hydronium. Just think of hydronium. It's kind of hard because I always think of hydroxide and hydronium. Hydroxide is OH, and hydronium is that acid ion. They're opposites. So you got to remember, if you're saying hydronium, you're talking about an acid. If you're saying hydroxide, OH, you're talking about a base. So what is an acidic anhydride? So, and a basic anhydride. So acidic anhydride is basically, hydride means it's combining in water with. So hydride meaning water. So oxygen can combine with the water to produce acid, and usually the acids come with non-metal oxides, right? And the basics are usually metal. So a basic anhydride is basically a metal, which is, the alkali metals and, columns 1 and 2 when you think of metals. One is in forming the acid, it's going to be a non-metal reacting. Water can either react as make an acid or a base, depending. So when you're combining water and you get, and it becomes an acid, usually it's from a non-metal situation, because oxygen can combine with different things, elements on the periodic table. And when you have a basic, it's going to be definitely a metal, and that's combining an ionic, and it turns it basic. So let's look quickly at these couple applications here. So we have identify the Bronsted-Lowry acid, base, and conjugate acid pairs. So let's just look at the acid. As we look at these, you can just see the conjugate pairs. You're going to have, here we have H2 and H3, a phosphate with phosphorus and oxygen. So here you're going to have a conjugate pair, which is, you're going to have as acid and a base. And here you have sulfate, and that's going to be another conjugate pair from an acid, to a base. So let's see if I... chromate is, oh, I guess I didn't really put number 1 there. Basically, you can see that there are the conjugate pairs in those two. Just remember there's conjugate pairs with the acid and bases. We went over those. Name the following compounds as acids. So you're going to, remember we were trying to name them. So this first one here is chromate. You have to look in that table on page 40, and this is chromate. So chromate, you would turn to what? Hydro-8 to ic. So it'd be hydrochromic acid. This would be hydrochromic acid with an IC, hydrochromic acid. This one here is hydrogen telubrine, and it's going to turn from to hydrotellurous acid. I'm not really sure about this one because I'm not sure about how if you pronounce it with the ic or not, but I think would be the OUS. So the next would be an oxalate. This is an oxalate here. It's turning this to hydrocarbonic, because we have a carbonic acid. Oh wait, yeah, this is number C. Let's make sure I'm on the right one. Yep, hydrocarbonic acid here, and so it's an oxalate. So you're going to say hydrocarbonoxylic acid. Hydro is 8 to ic. So let's go on to this one. You have sulfide, hydrogen sulfide, which is going to turn to ide is OUS, hydrofluorous acid. Here you have a sulfate. This is sulfate here. It's going to turn to this would be hydrosulfate. It's hydrogen making it an acid. So this would be, whenever the hydrogen's making it an acid, the sulfate is right, SO4 is sulfate. So you're going to have hydrogen sulfate. So it's going to turn to hydro-8 to ic, right? So it'll be hydrosulfuric acid, ic. This is hydroboric acid. This is borate. This is here, it says borate. So it's going to be hydrogen, hydroboric. Here's hydroboric, 8 to ic, right? Just, if you're going to have ic or 8 at the end. So let's go on to number 3. And number 3 is identify each of the following acids as monoprotic, diprotic, or triprotic. This is an easy one because we look at the hydrogen, right, the first. This would be what? Mono, because it's only one. This would be tri, because there's 3. This would be di, because there's 2. This would be mono, because there's 1. This would be di, This would be mono, this would be mono, this would be what? Mono. So although it has another hydrogen here, you always look at this first hydrogen. So predict whether each of the following is acidic or basic anhydride. Okay, if it's acidic, it's oxygen combining with a non-metal. If it's basic, it's going to be hydrogen combining with metal. So you have to look in your periodic table. Where is magnesium? So I looked at your magnesium, and you see where magnesium is on there. You see basically magnesium is going to be basic because magnesium is a type of metal. So it would be anhydrite because it's basically a metal. Sodium is going to be in your first column. Sodium's considered metal, even though it doesn't look like metal, but it's considered metal in that first column of alkali and alkali metals, right? In the first columns, those columns. So this is going to be what? It's a metal, so it's going to be basic. So this will be basic. This will be basic. Now we look at phosphorus. Phosphorus is not. It's a non-metal. So it's going to be considered acidic. When you look at phosphorus in the table, it's not going to be considered in the metal part. You just have to look in your periodic table. I could show you on the periodic table, but you should already know that. Let me show you. Move it over here real quick. You see sodium's over here, and the alkali metals here, magnesium. All of these would be turned to a basic. And in the other section, if you have oxygen of any of these on this side, it's going to be acidic, right? And so we have oxygen, here's phosphorus over here. Oop, can't see it. Can you? So here's oxygen and phosphorus over here. So if it's over here, it's going to be acidic because it's going to be turning non-metal. So metals are going to be basic. Basically oxygen can react with both metals and non-metals. So we're going to go ahead and quit right there on this, and then we'll go into the next section.